everyone. Welcome to the 9th bootcamp today with Classiq. So those who are joining us just today, I would recommend scrolling through the YouTube playlist and going through all the 8 amazing sessions we have had in the past with Classiq. Today we have with us Tomer Goldfriend from Classiq. Tomer is a theoretical physicist by training and holds a PhD in physics from Tel Aviv University. He used to work as a postdoctoral researcher at École Normale Supérieure and the Weizmann Institute of Science before joining Classiq as a quantum algorithm researcher. And today he is with us to discuss Hamiltonian simulations on a quantum computer. Very exciting, and over to you, Tomer.
Thank you very much for the introduction. Yes, so indeed I will tell you about Hamiltonian simulation and how to implement it in general, but in particular with Classiq. And this is essentially my plan. I will start with some introduction and motivation, and then I will go immediately to 2 different way to implement Hamiltonian dynamics. One with product formulas and another one which is based on block encoding. And the take-home message will be first that Hamiltonian simulation is a fundamental quantum primitive, and of course the 2 practical ways to implement will also be a take-home message. Okay, so this is essentially where everything started. In May 1981, at MIT, there was a conference which was called Physics of Computation. Here is a photo of many of the participants. So you can see many of our heroes. You can see the physicist Freeman Dyson and John Wheeler. There are also the computer scientists, Tommaso Toffoli and Edward Fredkin. So they are sitting right next to each other. And I also drew the quantum gates named after them. So this is the Toffoli gate and the Fredkin gate. And of course, you had Richard Feynman there. So in this conference, Feynman gave a lecture whose title was Simulating Physics with Computers. I know that the WOMANIUM is also not only about this course is not only about this session is not only about quantum, but also about AI. So I found this nice quote from Feynman's lecture. He said, "We never really understood how lousy our understanding of languages was, the theory of grammar and all that stuff, until we tried to make a computer which would be able to understand language." So what Feynman was looking for, and he said it was pushed by Edward Fredkin, is to understand how to simulate physics with computers. And during his talk, he mentioned the idea that can we do it with a new kind of a computer, a quantum computer. Okay, so the first quote is an example of things that he mentioned that computer science helps us to advance. So maybe, yes, so I will start now with maybe the most clear and basic and simplified definition of what Feynman was looking at, and this is Hamiltonian simulation. So I will define the object that essentially will be the main object that I will look at in my talk. We have an Hamiltonian, which is an Hermitian matrix, and we have time, which is a real variable, and then e to the minus iht is a unitary matrix. Okay, this is just basic mathematics. So if it is a unitary matrix, then why not implement it on a quantum computer? Okay, why that we will do that? It's not that every time we see a unitary around, we are going to implement it on a quantum computer. There are several reasons. First of all, there is the prime reason by Feynman, just to simulate quantum systems. Or as he said, because nature isn't classical, and if you want to make simulation of nature, you would better make it quantum mechanical. So this is the primary reason. But since this, of course, quantum computing evolved and many quantum algorithms and applications appeared, and actually Hamiltonian simulation appears in many of them. So I named here a few, and I'll give some references at my final slide. So first of all, people use quantum phase estimation to find ground state of molecules. This uses Hamiltonian simulation. also for solving linear equations such as the HHL algorithm, for solving partial differential equations, for propagating in continuous quantum walks, and as Rolando said, presented in the previous talk, in simulating coupled classical oscillators. So the main point here is that Hamiltonian simulation is a quantum primitive, and actually it underlies many of the expected exponential speed up in quantum algorithms compared to the classical ones. Okay, so this was for the motivation. Now, how we are going to do this? This is not that easy. I mean, it's not completely straightforward. First of all, the problem is really Hamiltonian dependent. I mean, you need to look at your Hamiltonian and understand how you want to implement its evolution. And usually the evolution, I mean, the implementation is an approximated one. And I'm going to show you two canonical ways to do this. One will be with product formulas, and the other one will be with quantum singular value transform. And one comment, a general comment throughout my talk, I will talk only about time-independent Hamiltonians, meaning that this matrix H is constant. Of course, in physics, it can also depend on time, but this is beyond the scope of what I will present. But most of the technique can be generalized to treat time-dependent. Okay, I'll start with product formulas. There are many different product formulas. For example, you have the Suzuki-Trotter formulas of the Q-drift. In Classiq, you can find Q-drift and Suzuki-Trotter. These are built-in functions. And under this path, under functions in the Classiq library, you can find notebooks that will show you how to use it. In my talk, I will focus only on the Suzuki-Trotter. Okay, so I'm assuming that my Hamiltonian is a matrix of size 2 to the n times 2 to the n, and that the Hamiltonian is given as the sum of Pauli strings. So any matrix can be written as a sum of Pauli strings. So what is a Pauli string? It is a tensor product of n matrices, n Pauli matrices, the 2 by 2 matrices. It can be the identity, the X matrix, the Pauli Y matrix, or the Pauli Z matrix. So the Hamiltonian can be written as a weighted sum of these terms, where alpha are just real coefficients. So you already from Eden learned about Q mod. So this is, for example, how I just describe, I mean, define an Hamiltonian in Q mod. Let's say I want this Hamiltonian, XX with a coefficient 0.1, IZ with coefficient 0.5, etc., etc. So we have a quantum struct, which is a Pauli term, and I'm having a list of Pauli terms. So you see the first one is XX with this coefficient, and this is a definition of my Hamiltonian. This is my object. Now, if my Hamiltonian is just a single Pauli string, for example, let's say my Hamiltonian is pi times ZZZXX, then there is an exact implementation, I mean a gate level implementation of its Hamiltonian simulation. This is how it looks like. You can see that it is composed of CX gate and RZ gate, which with the time. So this is a parameterized evolution, and you have the H gates, which are actually related to the X. Okay, so this is exact. We know how to implement this on a quantum, as a quantum program. Now, what about the case where you have a sum of two Pauli strings? So with matrices, the exponent of the sum is not necessarily the product of the exponents. Okay, so this equation does not hold unless the two matrices commute. So if P0 times P1 minus P1 times P0 is equal to 0, which means that they commute, then you have inequality. But this is a very specific case. For example, here it is true, but I can replace Z by X, or by y, and it will not hold. Okay, so we cannot implement this as a product of these two unitaries. And this is one of the facts that essentially we resort to approximated implementations when we look at Hamiltonian dynamics. And one of the approximations is given by the Suzuki-Trotter product formula. So what are these? The Suzuki-Trotter formulas refers to a set of formulas. Each formula is an order O and a repetition R. Okay, so I'm going to designate them like this. I mean, the Suzuki-Trotter with order O, repetition R, and time T, it tries to approximate this evolution. And of course, the idea is that when the repetition goes to infinity or when the order goes to infinity, you converge to the correct, to the exact evolution. So how does the Suzuki-Trotter of order 1 looks like? It is essentially just taking the product of the single Pauli exponents. Okay, so instead of the sum, I'm taking the product of a single term. This is order 1 and repetition 1. If I want order 1 and R repetition, so the idea with the repetitions is that you partition time by some factor. So I partition time by R, and then I'm repeating my formula R times. Okay, so here, this is Suzuki-Trotter with time T over R, I'm repeating it R times. Okay, so if you like, I told you before that this equation does not hold. I mean, there is an inequality here in general. And the first order Suzuki-Trotter says that, okay, let's approximate this by that. And if we go to higher order, so for example, order 2, you divide time by 2, and then you take the terms from L to 0, and then the terms from 0 to L. And you can also define higher orders, which are 2L, so you can define fourth order, sixth order, etc., etc. And this is defined recursively. So the fourth order comes from the second order, etc., etc. On purpose, I didn't write the full formula here. It's just, I mean, it's not that long, but I think it will not help too much. You can find it, for example, in this reference, and if you really like, I mean, we can, I can send it, but it is essentially, this order is defined from the previous order. And again, with repetition, for each order, we have a repetition. So we can refine our approximation by taking higher and higher repetitions. Okay, now these are the formulas, but how I actually implement them. So first of all, one thing to understand is that if I have an Hamiltonian and I'm looking at this function, its approximation of some order and some repetition, there is an exponentially different ways to implement this as a quantum program. I mean, there are exponentially different ways to decompose it to Cx gates and to rotations. And Classiq has Suzuki-Trotter as a built-in function, and this built-in function already provides you an optimized implementation, which reduces the Cx count and the function depth. Okay, so this is, for example, how I would call Suzuki-Trotter with my Hamiltonian that is defined here. This is the evolution time t, and I'm doing order 4 and 1 repetition. Okay, so this is a built-in function, and it is, as I said, it has, compared to just, I mean, trying to write it yourself and choosing some different implementations, then in our case, the Cx count will be reduced by quite much. And again, under this this path, you can look at more examples. Okay, so I told you that we have a formula that approximates our evolution, but I didn't say anything about how good the approximation is. I just said that higher order and higher repetition will give you better approximation. But of course, usually we're interested in more precise questions and answers. So let's say I want an epsilon approximation, and then I ask, an epsilon approximation for my Hamiltonian dynamics, and then I ask which formula should I choose. Now this is not that, not an easy question. There are several papers that treated this question, and in particular, the literature, what people give in the literature are theoretical bounds for the errors of these product formulas. For example, you can look at the distance between Suzuki trotter with repetition R and order 1 and R repetitions, and ask how far is it from the real evolution. And here is a bound from the literature, and you see that it goes as t squared as 1 over R, meaning you can see that as R goes to infinity, indeed, my error gets smaller and smaller. And this bound is actually good because it takes into account also the commutation relation. So this is, you run over all the commutation relation between the different terms in your Hamiltonian, the different Pauli strings, and you can see that if your Hamiltonian consists only of commuting elements, then the bound is 0 and your formula is exact. So again, I choose not to really go to the mathematical definitions. You can find it there. In this last paper from 2021, I think it has it provides the best bounds that are known, and it also gives not only for Suzuki trotter, I think also for Q-drift, but yeah, I think also for Q-drift. So you can find it there if you want to read more, also for higher orders. But again, this is not, you need to really define it mathematically, and I didn't go into the details, but usually you can ask what is this distance is, and people usually look at the diamond norm, which is a norm for quantum channels. Okay. So this was for the product formulas. I will go back to it in the end when I will present, maybe say a few words about Q-drift maybe. And now I want to move to the other technique, which will be based on QSVT. And it is related to block encoding based in approximations. In this path, you can see a notebook, Hamiltonian simulation with block encoding, and there you can see implementation of these two techniques. I will focus only on the QSVT one. Okay, so I will assume no previous knowledge on block encoding. So actually this part of my talk will be a crash course on block encoding. And so I'm going to show, three points that eventually will help me to build the algorithm. So you will see it will be very hierarchical, and I will try to explain each and every step, and eventually we will tailor everything to Hamiltonian dynamics. So this is a definition. I have my Hamiltonian matrix, which is 2n by 2n, and an S capital M block encoding of this matrix refers to a unitary matrix that looks like this. Okay, this is how I designate it. This is a block encoding SM of H. It is a bigger matrix where on this diagonal we have H, which is 2n by 2n, and let's say I completed it to be unitary with another 2 to the m dimension. Okay, and this matrix is unitary, and S is this factor. Okay, so this is the first thing. And the idea is that if I apply this unitary on some psi 0, then on this part of the vector I have H psi. If you write it with bracket, what you will find is that if you apply it on psi, so psi is of size n, and this quantum variable is of size m. So if I apply it on this, then the 0 part will be coupled to H times psi with some garbage. Or maybe, let me show you like this. Let's say I have my block encoding function, which is some block encoding, okay? So it's a black box. It has two variables. It has one variable for the data for this part, and one variable for the block, which completes it to be unitary. Okay, so my block encoding here, this is my block encoding. The data part is of size 2, meaning the Hamiltonian is of size 2 to the power of 2 to the power of 2, and I have a block variable, okay, which is of size 3. So I allocate the block variable of 3. Let's say I have some amplitudes that I'm loading to the data. So this is, I'm preparing some psi. Then I'm applying my block encoding. So psi connects to the data part, and the block starts with 0. So what the block encoding gives you is that if you post select the block variable of size m to be 0, then you know that this state is proportional to h times psi. Okay, this is the idea of block encoding. Now for the second point, let's have several block encoding unitaries. So I have a block encoding of A1, block encoding of A2, etc., etc. Then what we can do, we can block encode a weighted sum of A1, A2, until AK. This is what is called linear combination of unitaries, or which abbreviated to LCU, or prepare and select. Okay, the idea is that I know how to, if I know how to block encode these, I know how to block encode a weighted sum of alpha of AK. And again, you can see the size of the block. I called it M bar. You can see how it is related to the problem, and beta bar now. The normalization coefficient is actually depends just on the sum of the beta case. So this is the second thing to know, that I know how to block encode weighted sum of unitaries. This is typically how it looks like. Let's say I have A0, A1, and A2. I mean, I know how to block encode them. So this is block encoding of A0, and this is of A2. And so typically what you do, this is the prepare and select. You are preparing amplitudes with beta. So beta over beta bar is a normalized vector. So you prepare the betas, then you're doing the select. So you are selecting the first unitary controlled of the prepare being 0. Then the first one, I mean, 1 of being 1, and 2 if the this variable is equal to, and then you do the inverse preparation. Okay, so this is how you, this is the LCU, this is how you can encode a weighted sum. So now I will show you how to do this in Q mode. Let's say, again, I have black boxes. I have 2 block encoding, one of A1 with a block size of 3 qubits, and a block encoding of A2 with a block size of size 2. And I want to block encode the weighted sum. So again, I need to prepare the amplitudes of these betas, which is FF. The way to prepare the amplitudes is just with the H gate. Okay, so I have one variable for the betas, for the prepare, and I need to do within apply, right? Within H, apply something. This is what you see here. Prepare and inverse of prepare. Oops. So I'm doing within apply H, and then I apply if the block, if this block LCU is equal to 0, then I'm applying my first block encoding, and if it is equal to 1, I'm applying my second block encoding. And you can see one block encoding is with m equal 3, the other one is with m equal 2. So for the first one, I'm using the slice between 0 to 3. And in the second one, I'm using between 0 to 2. And what eventually do I get in the end? If I post select on the block, on the original block, and on the new added block, I know that here the state is coupled to A1 plus A2 times psi. Okay, and of course, I mean, in Classiq, sometimes some functions uses auxiliaries, and you don't need to care about this. I mean, this is done automatically. Okay, and now for the third part, the quantum singular value transform. This is essentially a quantum primitive that implements block encoded polynomial of a matrix. What do I mean by that? Let's say I have a block encoding of size n. I mean, my age is 2 to the n, and my block size is m. Then the QSV technique gives you a block encoding of some polynomial of h. Okay, what is the characteristic of this block encoding? It adds one more qubit to the block size. So now the block size is n plus 1. And okay, you have also might have another factor as prime, and p is a polynomial with a given parity. So this is one of the things that QSVT gives you. And this is how typically this looks like, a QSVT. So if I have a polynomial p of x, to apply QSVT, what you need to do is to first calculate some rotation angles, I mean classical rotation angles that will be entered into the QSVT routine. These are the angles that are related to the quantum signal processing, and you can do it with an external library, PyQSP, for example. So you want to implement your polynomial. You say which polynomial you want, then you get the angles, and then the QSVT essentially is a series of applying your block encoding and rotated reflections. So it is block encoding, rotated reflection, block encoding, rotated reflection, etc., etc. And the reflections are the rotation angles are the angles that you calculated from the beginning. So essentially, you have 2 to the n rotations if you want a polynomial of degree n. Okay, and again, you don't have to worry about constructing it yourself. We have in our open library, we have a QSVT function. Again, under functions, under QMod library reference, Classiq open library, you have a notebook. And in this notebook, you will see how to call this function. And we also have 2 algorithms that are calling this function. One is to find the fixed point, and the other one is for applying a matrix inversion. And again, I want to emphasize that essentially this is a block encoding. I have my initial block encoding function, and I plug it into a QSVT, and this gives me a new block encoding with another qubit, with another block qubit, and I know that the data will hold my polynomial times psi times when I post select of the others being 0. Okay, and again, this psi is something that I started in the beginning on the data variable. Yes, okay, so that's it. We are all set to approximate our Hamiltonian dynamics. Let's see how we are going to do this. So first, you need to block encode your Hamiltonian. Until now, I didn't say how to do this because there are many techniques to do this, and this is just one block in the algorithm that you can, which is flexible. You can choose how to block encode your Hamiltonian. I will show it soon. I mean, I will show one way to do this soon. And so assume that you have your block encoding Hamiltonian. The second thing you need to do is to find the QSVT angles for approximating the polynomials cos xt times s and sin xt times s up to some desired precision epsilon. Okay, you can approximate this by polynomials such as the Chebyshev polynomial. Okay, so once you have your angles, you apply QSVT to get the block encoding of cos ht and the block encoding of I sin ht. Okay, I added to the notation here epsilon. Epsilon is because this block encoding is not exact, right? I'm having a polynomial which approximate this and approximate that. So I have here 1 and 1, which is the factor, and n plus 1 is, again, I'm adding 1 block qubit to my block encoding dimension. So I have these two, and now I can do LCU to get the sum of these. Okay. Now I can do LCU and get the weighted sum of these two things, which is e to the IHT divided by 2. Okay, so now I have an approximated block encoding of my Hamiltonian dynamics. It has a prefactor of 2, this is this F, and m plus 2 is the dimension of my block. Okay, this is how it looks like. I have a QSVT for the cosine, I have QSVT to I times sine, and then I'm doing exactly what I showed you before. I'm doing LCU, I'm doing a block encoding of the sum of these. Okay, so if this variable is equal to 0, I'm applying this QSVT, otherwise I'm applying this one. And if I post select on the other qubits being 0, I know that here I have an approximation of e to the IHT. So this is how you apply Hamiltonian simulation with QSVT. So it is important to know that the depth is dictated essentially by the number of rotations that you apply with the QSVT, which in turn depends on epsilon. Or the other way around. Usually you say, okay, I want an epsilon approximation. I will generate a polynomial for sine and cosine according to this approximation. And this will tell me how many angles I need to have. Okay, one slide about block encoding Hamiltonians. One way to block encode Hamiltonians is actually with LCU. So if your Hamiltonian is given as a sum of Pauli strings like this, so you can block encode it with the prepare and select. What you can do prepare this alpha. So I have here 4 alphas, so I need 2 qubits. Okay, so I prepare a state which is alpha 0, alpha 1, alpha 2, alpha 3. And then I'm doing the select. So the idea is that I, Z, X, and ZZ, they are all unitaries. So I'm doing this unitary, then that unitary, etc., all controlled on this state. Then I'm doing the inverse, and actually this is the block encoding of my Hamiltonian. But of course, depending if your Hamiltonian is sparse in the elementary basis, maybe you want to block encode it differently. So for a given Hamiltonian, you need to think how you want to block encode it. Okay, so let me summarize. I hope I convinced you, at least in the beginning, that Hamiltonian simulation is a quantum primitive that appears in many quantum algorithms and applications. There are many ways to implement it, and all of them are essentially approximated. I showed you in detail I think the most common ways to implement Hamiltonian simulation, which is Suzuki-Trotter and QSVT. Of course, there are others. One is Q-drift, which is essentially a random product formula. So instead of taking the deterministic Suzuki-Trotter, you're doing something which is random. We have it in our core library. This is the original paper. Since then, people worked on combination of Q-drift and Suzuki-Trotter. So some part of the Hamiltonian you're doing with Q-drift, some part you're doing with Suzuki-Trotter. And in this paper, they also calculate the error of this. And there is also qubitization that you can see in our notebook. It's maybe less efficient, but I think educational it's a very good one, and it might be efficient in some cases, I believe. And finally, there is also Taylor series. You can find it in this paper, which is also, I mean, also a technique, I think less common, but still technique that probably is good in some cases. And as I promised, here is references to some quantum applications and algorithms that include Hamiltonian dynamics. Before the detailed ones, in general, I think this is one survey of applications and then end-to-end complexities of quantum algorithms. And there, I think it will be easy to navigate to see which algorithms are using Hamiltonian dynamics, in which of the algorithms the Hamiltonian dynamics is the crucial part. So I think it's a good survey and very easy to navigate in. So this is in general for quantum algorithms. But for Hamiltonian simulation, in continuous quantum work, you have this paper, you have in solving PDEs, such as solving the Poisson equation, finding a ground center of Hamiltonian, and also the last talk about simulating coupled classical oscillators. And that's it. I finished. Thank you.